Изобщо няма да дигнеш нищо.
Good, well, morning, afternoon, evening, everybody, depending on where you are. Very welcome to this presentation, and I'm glad that you're all here. My name is Matthias Schmidt. I am the CEO of AnalyzerPro, and today we are going to try to get a brief, small overview about the capabilities of AnalyzerPro together. We are going to work on a few cases. We will try to get a little bit into the detail. Of course, you can imagine that Analyzer is a pretty large piece of software, so we will have no chance of covering it all today. However, I guess we will have a few things that might be interesting for you. I've prepared several examples, and at the end of each example, you will have time to ask some questions. And yeah, and with that said, I think we can get going immediately. So let me just remove this splash screen. No, I don't want to save that PowerPoint. And start with our first example. So what do we have here? We have a case here where the driver of this blue car, it's a Volkswagen, wanted to go over here and park in this area. This is a well-known cafe. And he came here, he slowed down, and then from, as at least what he said, from a standstill, he tried to drive over there. Unfortunately, that was not possible for him because at the same time, a red car over here, I think it's a Volvo if I recall correctly. Let me check. Yeah, it's a Volvo. Came here. They met somewhere around these lines, and yeah, these are their final positions. We don't have much information. The police secured the final positions. We have very little and actually not very good photo material. And I guess depending on where you're from, you might be used to that. So I can show you two pictures. This is the Volvo. I don't even know if you can properly see it right now because it's a like very bad picture. Being damaged here on the front, and then we have the transporter, the Volkswagen transporter, being damaged in the rear. And our question is now, how can we deal with that accident? And how can we work on a case like that? So you can clearly see I have prepared a little bit because I didn't want you to watch me putting in all the measurements of the police and so on. But still, we have a few things that might be interesting for you to discuss first. So when you start a case with Analyzer, the first thing you're usually going to do is you are going to put in the vehicle data or the participants of that accident. I've prepared that already, but just to show you a little bit how it works, you open this window. You could put in all the data manually, but usually what people do is they just use the integrated database. It comes like, I think, over 6,000 vehicles by now. And yeah, with some of them with 2D DXF and 3D models, some of them without. That's a little bit depending. And yeah, so essentially in the first step, what you do is you define all your participants. It's very much straightforward. I can't tell you much more about that. You search for your vehicle, you select it with a double click, you have it. I have prepared Volkswagen, the transporter, and the Volvo. In a second step, what you usually do is you bring in your sketch in one way or another. So you could draw something directly with the drawing tools on the left-hand side. You could put in some photos just by drag and drop. You drag them in and they are there. We have a module here that allows you to access Google Maps, for example, and you can directly access that data. Or, and that's probably more or less the most common thing nowadays, you use either 3D photogrammetry or laser scans. Analyzer can read in this data. So either, it actually doesn't matter if you take a 3D photogrammetry or a laser scan file. They both work the exact same way. You read them in with Analyzer. There's a window for that. And it will create you a 2D image as well as a 3D landscape without any additional things to do. There is no need to do some triangulation and so on. And that's what I have prepared for here. So this 2D image that you can see was actually automatically generated out of a laser scan, or no, I think in this case it was a 3D photogrammetry, but doesn't matter. And when I open 3D now, we can see that at the same spot there is the street. The scanning was directly imported. There's no magic behind it. Yeah, so we have all these different ways, approaches, how we can input our sketch data into Analyzer. Right now, not much is happening there. It's only the landscape, and therefore I'm going to close it again, but you know it's here already. Okay. These steps are usually done within a few minutes. There's not much more to explain about it, actually. It's as simple as I just said. Good, but back to our case. So I don't know how it is for you, but when I encounter cases, it quite often happens that we have very limited information about the case in general. So we need to think a little bit how we could solve that, how we could work on that, and yeah, and I think we can do that right now. So we have a piece of information that might be interesting, and that is that the blue car stood here and wanted to go down there. So the first thing I'm doing now is I am just drawing some imaginary line that should indicate how the driver, or how which path the blue car would have taken if it was uninterrupted. So I'm just taking this spline curve. I'm making like a rough curve, how a typical driving procedure of such a car would have looked like. So he would have come from here, gone down, and then gone down from there. Why am I doing this? Because that gives me roughly an idea where the car would have been at collision point, because we don't have like good traces, we don't have any other video footage or whatsoever in that case, so we don't really know where the collision happened. I mean, it's clear it has to happen somewhere around here, but we don't know where exactly. But with that, we can roughly, at least very roughly, estimate how the blue car has gone. On the other hand, we know that the red car has come from this side, and so yeah, they must have hit somewhere around here. And what I want to do now is I want to do a collision analysis. So I would like to find out the collision speeds of the two cars, in order to then continue with the pre-collision analysis. And we can do a collision analysis in several ways in Analyzer. That which one we're using is a little bit depending on the situation, but for most cases, what we can do is momentum forward calculation. And I would like to show you today the automatic collision analysis. That's a tool we have for several years right now. And I think I'll just show you how that works. So I'm opening the module. And you can kind of clearly see what to do. There are numbers 1 to 5. That means you have to go through these points in this order. So the first thing, probably the hardest here, is specifying the collision positions. So I'm clicking on that, and I get the two shapes of these vehicles, the blue one and the red one. So I'm making a little bit of a guess for the blue one. Again, this is a hypothesis that doesn't have to be exactly that way, but when we maybe a bit steeper already, like when we position it a little bit like that, it should be, at least idea-wise, roughly how it would fit to our imaginary driving line if nothing had happened. And well, the second one is, again, let's call it an educated guess. So something around here. Please note that we have to go into a decent overlap because that's what the momentum theory requires. I could go a lot into detail here, but that would kind of take too much time right now. So again, I'm taking an estimation of the collision position. This doesn't have to be the right one. This is just an idea I make based on how I perceive the scenario. When I'm done, I click on finished, and I can continue to number 2, specify end positions. So this is a rather easy task. I just take my two vehicle shapes and place them. Oh, sorry, I didn't want to move that one. And place them where the vehicles should end. So the blue one and the red one over there as well. There we go. Okay. Then I have to continue with my parameters. So I open that window, and essentially what I have to do now is I have to tell Analyzer what I know and what I would like to know. So first things first, the tangent, we don't know like the location of the idealized impact point. We don't know usually. It has a huge impact on the calculation. So I would just always let that vary or find out by the algorithm. We could give it a total range for the collision location if it was like very a large range of possible final possible collision locations. But in order to save a little bit of time, I'll just assume that this is roughly the collision location. Again, we will give it a bit more variation later. K value, that's the value that defines how elastic or plastic the impact is. For typical collisions, this is a rather useful rather typical range between 0.05 and 0.3. Coefficient of friction between the two vehicles, we could either give it a range or we can give it a fixed value. Since this is roughly a 90-degree collision, the coefficient of friction actually has very limited influence. So it wouldn't matter much if we let it vary or if we give it a fixed value. So we can leave it a fixed value anyways. Okay. So speed of vehicles. Well, the good thing is the algorithm can kind of cope with any range we give it. So it could deal with, don't know, 1 to 200 kilometers per hour, and that wouldn't matter much. I guess we can make it a little bit easier for the algorithm right now, since the blue car was standing over here and then accelerating. it was probably not that fast yet. So I guess something between 5 and 30 kilometers per hour should be a decent range. For the red one, we do have, like the driver said, that he was going with 60 kilometers per hour, which is funny because there is a speed limit of 50 kilometers per hour, but okay. We don't really know it, so I would just give him something between 30 and 90 or something like that. Yeah, again, it wouldn't matter much. Braking, we don't know. This is braking pedal position, so between 0% and 100%. So I just say something between 1 and 90%. The 1% is because, yeah, we give him some minimum deceleration due to braking, maybe. Again, especially for the blue one, this wouldn't have much influence in this case because the most deceleration will come from the rotation that it does counterclockwise over there. But for the red one, it will have a large influence, I guess. Steering wheel. Well, yes, I'm relatively sure that the blue one had steered because he wanted to go over there. So there was surely some steering involved. So a positive value is to the left and a negative value is to the right. So we can definitely say he was not steering to the right here. So it's at least 0 to, and then I would just give it the maximum upper range. Please note that this is the degrees of rotation of the steering wheel, not of the wheels themselves. For the other one, maybe he was going slightly to the right because he would try to do some evasive maneuver. I will give him something like maybe -100, which is to the right, to maybe 0, because he was surely not steering to the left. We would see that. Let's continue relative position. So it could be, since we did estimations here, that our collision positions are actually not correct. Could be a little bit further, left, right, up, down, a different angle, and so on. And so I would just give it a little bit of a range for the relative position to each other, maybe some like 5 centimeters or whatsoever, and maybe, yeah, 5 degrees or something like that. Okay. With that, we have given the algorithm the values we know, which is not a lot right now, and the ones we want to know, which is, yeah, quite a few. And in the next step, I'm going to click on Calculate. So this is usually the part that requires the expert to take a little break, get himself or herself a coffee, and yeah, enjoy the 2 minutes of watching a computer doing the hard work. Because what's happening now is that Analyzer is doing a momentum forward collision analysis, and every number that counts up here that you can see is a full simulation. So collision simulation and then run out simulation in the end position. And it will do that as long till it either finds a very good overlap between the wanted and the calculated final position, or at some point, if it can't find any overlap, then it will stop as well, because it could be that under the given parameters, there is no possible solution, of course. And it will do this task not only once, but it will do it 10 times and completely independent from each other. And there's important reason for that. So you have just seen that there are a lot of values going into collision analysis, and or like a lot of input variables that you could put in. And theoretically, it is possible that a certain combination of values would lead to a desired final position, but it could also be that another combination of values would lead to the desired final position. Imagine a situation where a car goes quite fast and brakes strongly, and a car that goes rather slowly and but only brakes weakly. So they both could end up in the same position. With these 10 independent calculations, we want to point out if there are such two sets of or several sets of possible solutions. On the other hand, it's a great way of giving you certainty into the results, because if all the results end up like around a similar range, you can be kind of confident that the real solution was also in that area. By the way, I can see right now that Zoom is draining a little bit my computer's capacity, because it should be done by now. But anyways, what is probably interesting here is this value called quality. So quality is a value that tells you as the user how close the wanted result and the calculated result match. And the best value you can achieve is 100. That means the calculated result and the desired final position like match perfectly. Please don't mistake that for a probability, because probability is something that you can't really have in a collision analysis like that, because 100% probability would be the exact final position, okay, but what would be 0? So don't confuse quality with probability. Quality is a value for you, the user, to understand, are my results going in a good direction or not? Because if they all would say quality 0, 0, 0, 0, that means there are no possible solutions with the given parameters, and then you would cancel it, the calculation, and change some parameters and try it again. You can see already some values here. So V1 is the speed of the blue one, V2 is the speed of the red one in their specific sets of calculations. But again, all this depiction is kind of only for you as the user to see that something is happening and that there's not just some like black box doing something. Yeah. An important thing to know about this tool is that this is not designed to be some kind of optimization when you have already done your collision analysis. This is to be used as a first approach, just very much like I did it now. I'm having some ideas about a collision position. I'm having some ideas about the final position. And in the end, I can start the algorithm, let it do the hard work, and then just visually select which solution I like best. Yeah, there is no magic involved behind that. All it does is just regular momentum calculation for the crash itself, and then run out simulation. So even if you would work manually with this tool, with collision analysis, you would do the exact same things. The only smart part that comes in is the optimization algorithm that works to find the best possible solution. And if you're working on very difficult cases, you can it can take quite some time to reach a goal. And with this, we're done within a few minutes. Okay. You don't have to wait till all the calculations are run through. If you see already a situation like this, where you have 99 quality value 99, 99, 99, 99, like you can see here, you can also just like cancel the calculation and keep the values you already have. So that's what I'm going to do right now. So he asked me, am I sure? Yes, I am sure. It will take a short while to process all the data. And then we have at least our 7 calculations that we have done right now over here. We see the results, we see an EES value, if you're familiar with that concept. And what I can do now is I can show, by clicking on it, which solutions we're getting. So I can take this one, I can take this one, and so on. And we always see the final positions, they're almost exact matches. We see how it placed the vehicles. And yeah, and then I can just select which one I would like to have. So I'm probably taking this one right now, and I'm clicking on transfer. That again does a short calculation, because what happens right now is that it writes all the data we are having into the manual collision analysis, as well as in our main data window. And I will introduce you to that immediately. What we just have now is this situation where the car is coming there and going over there. Good. So I threw a few concepts at you now, but just to sum it up, that's how the automatic collision analysis works. So we put together our initial positions, we put together our final positions, we set a range of parameters, and we let the computer do the work. It calculates, it gives us different options that we can choose. And then it writes the data to our main data window. So the main data window, this is this one. And that's where all the calculations of all the vehicles and everything we do comes together. It's a kind of an overview window. It works, we can calculate directly in it. But also if you use any module, all the calculations will end up here. And that's kind of a brilliant concept because it enables us to use different techniques, approaches, and put them all together one after another. So that makes it quite efficient. Okay, so yeah, we now have our result: collision speed of the red one, 57 kilometers per hour. For the blue one, 16.4 kilometers per hour. But of course, the collision analysis is only the first step for a proper reconstruction of an accident. So what we need to do now is we need to do a pre-collision analysis because we want to know how the accident happened and why and so on. And for the blue one, I think we can again use a module. And the module I'm going to use is a turning procedure module. It's essentially just designed to let cars go around curves or whatsoever in a very smooth way. You can let the car accelerate in the process, and so on and so on. So we have to go through these values, and the others will be calculated for us. Initial radius. Well, when the car was standing up here, it didn't have any radius, so that's 0. The final radius. So which radius did the car go? And I will help myself for a second with a little circle that I'm placing here, just to roughly estimate the radius of that movement. Maybe a little bit bigger even. Yeah, something like that. Look at the properties, see, okay, that's 30 meters diameter. So I can just take a radius of, let's say, 15 meters for this movement here. Steering time, we don't know, but like it steers quite a bit, so, or he or she steers quite a bit. So I'd say like 1 second, 2 seconds, something like that. Again, we are in the hypothesis phase, so we are making hypothesis, and this is kind of a normal angle. And the maximum yaw angle, so compared from starting to finishing, get a rough estimation, that would be, I'd say, roughly 30 degrees that it turns from here to here. But again, we will change that afterwards. So I'm giving it 30 degrees. Initial velocity, well, is said that there was a standstill here, so 0. Acceleration, well, in a situation like that, you probably might want to go over rather quickly than slow. So maybe let's give him an acceleration of 2 meters per square second or something like that. And I can click on calculate. So what happens now? We still see a lot of values that pop up, a few in between values, and we see that a nice and smooth driving line forms over here. And probably our result is like kind of good, but not perfect, because maybe he was standing a little bit further down. A great strength of Analyzer is that you can increment values and it will immediately adjust everything around it. So it will adjust the driving line, it will adjust the other values, and so on. So I could, for example, make the radius a little bit smaller. So I click in here and I just increment it down, and you can see how the radius gets a bit smaller. And I could do that with each and every value whenever I work with Analyzer, and I will immediately see all the effects of values that I increment. That's especially useful when I don't know exactly where to search, or I only have a rough idea where to search, and then want to try around and see which value influences which result. But yeah, I think that looks kinda good in that way. So it starts from here, he accelerates, and then he gets hit by the other one. Nice. So let's have a look at the red one now. The red one must do a few things, or will do a few things. He will react, will have a build-up time, a build-up phase, and you might have a braking phase. So let's see what the visual situation could help the red one to react and use that to find out the pre-collision behavior of the red one. So, I mean, this is of course now a little bit depending on the situation. We could say, okay, when is the red one, like when is the blue car visible for the red one that he actually moves over there? We know that he had a blinker on, so it's probably definitely earlier than down here. Maybe something around here or something around here when he had the blinker. We could say something like this. He's a bit on the other side of the road. He has his blinker on. We will switch it on afterwards. And yeah, so we could say, okay, maybe when the blue one was here, the red one could have reacted. If we take a little look down here, we see this is 1.3 seconds before the collision happened. So we now have a total time of 1.3 seconds for reacting, for build-up phase, and maybe a small braking phase. And we can do that with another module called Calculate Path Time. I'm selecting my vehicle number 2 and selecting the first free phase. That will go too much into detail. But essentially what we have here are a lot of values. So, and for calculating this whole process of reacting, build-up time, and braking, we need 5 out of these values. So fortunately, it's easy that the reaction period, well, depending, but usually we say something like 1 second, 0.8 seconds. That's yeah, a bit depending on the legal system you're in or what you used to work with, but you can change that. But I think 1 second is a good default value. Build-up time, so the time that it takes till the brakes fully apply their braking force. Typical value is 0.2 seconds. We know the final velocity, meaning in that sense the velocity where it comes into the collision, because that's what happens right after that process. And that is taken automatically from our main data window. We don't have to mess around with that. We can't even if you want, you can't mess around with that. So that's our result from our previous collision analysis. So 57 kilometers per hour. These are 3 values. We need 5. So we just said, okay, the reaction started 1.3 seconds before collision. So the total time for reaction, buildup, and brake is 1.3 seconds. And then we could assume like a deceleration, full braking, which is a typical value, like 7 meters per square second or something like that. Of course, depending if it's wet, if it's dry, and so on. I'm giving him 7 right now. And I can click on calculate. That will give us a few more results. So that gives us an initial velocity of 62, a very short braking distance because he doesn't have much time for braking, or very short braking time as well. A total distance for the reaction, build-up, and brake of 22 meters. And a missing braking distance that could be interesting as well of 18 meters. So if the red one had 18 meters more, he would have had a standstill under these given conditions. Okay. So what I can do now is I can adjust my driving line a little bit. I can put in further points because I'm pretty sure he was not going like this, but maybe something like this, and like this, and maybe a bit further down like this. And we can also automatically synchronize the driving behavior because now our blue car is moving and the red one is doing nothing before because we haven't given him any data. I can do that automatically by just clicking on that flag symbol, which will make the red driving line a little bit long, as you can see. And we kind of have our full pre-collision movement here. Can now make it a little bit prettier, switch off the final positions, delete this helping line, and we have the car going, and colliding towards the end position. I mentioned earlier that we have a blinker, so I'm just clicking on the car, going properties, and putting on an indicator to the left, just for a random period of time. So for the whole time, and we can see, okay, now we have our movement behavior. Don't know, you might see it a bit by zoom, but a bit not super fluent, but I guess you get the idea. We can also now look at it in 3D. Oh, I forgot to load the vehicle file. Oh, that's a pity. Give me a second. I will fix that. So we get a nice file, a nice 3D model. I think I saved it here. Nope. Nope. Okay, I haven't saved it here. Then let's search for the model in the database. Oh yeah, here it is. So we take this one, and the Volvo I also can search in database swiftly. So let's take this one. Perfect. And that actually looks kind of smooth now. So we have our two cars, and they're going, blinking, they're colliding, and going into the final position. Please forgive me that you might see this like in a bit not super fluent way, because that's usually Zoom's fault that slows down my computer. But yeah, I guess you get the idea. And yeah, that's kind of it with the case. However, I am aware that most of you actually have to give written reports. So of course you can take screenshots, you can make videos of this. There's a video tool here. You can also make a video of the 3D, of the 2D, I mean. But there's also a function that gives you the full report in a written way, and that's this tool called Create Report. I select for which vehicle I want to do the report. Maybe for vehicle number 1, I click on Create, and I call it my report or whatsoever. Save it. It takes a short while, and what will happen now is it will create a PDF. You can see it here with all the input data and all the formulas that lead to it, because I know, or I have witnessed it several times, that let's say some lawyers or whatsoever, or opposing experts, are trying to like attack your work and your calculation and say, okay, what does it calculate and the backend and so on and so on and so on. So what we came up with is this report feature that gives you not only the values, but it gives you also all the formulas how to get to these values. So everybody who is capable of holding a calculator can double check that. You can see data in like a higher resolution, how it changes. You can see the vehicle data that was used. You can see the collision data. You can see the formulas for the like the double check formulas for the collision. So this is the momentum equation. This is the energy equation. They all have to have the same results. Of course they do. So with that, you can easily show critics what you have done, how you have done it, and so on and so on. And as you have seen, it's just a mouse click to do that. Okay, that was our first example. If you have any in-between questions, please speak out or write it into the chat. I'll try to answer that. Okay, there is a long question. Is there an option to weight certain items? For example, in mathematics, we can state the result positions at the point of impact are near absolutes because we have solid evidence, and the paths weights, these are all yeah, well, so the question is about if there is yeah, in automatic collision analysis, if there's a way to weight the results. And there is. So on one hand, if you know it with absolute certainty, you just give the value and say that's a fixed value, let's not vary it. If you have only a small range, just give it a very small range. It will always stay in that range, and that's how you can weight it. Is the coefficient of friction in the input phase for vehicle this vehicle or the road interface, unless I missed it, I didn't see the coefficient of the road. Yeah, the default coefficient of friction of the road is 0.8, but of course you can change that. Is there an option for trailers, caravans, and or defected braking systems? I guess this question still refers to the automatic collision analysis. So the braking behavior doesn't change if you have a different type of vehicle in that sense. So if the braking system is defected, you would just allow it less braking or no braking or whatsoever in the data. The only point here is there an option for trailers? No, the automatic collision analysis right now doesn't work for trailers. Will at some point in the future, but right now it doesn't. Okay. Any further questions right now? Oh, blue line appeared here. That's interesting. Good. If there are no more questions, we can continue with the next example. I just see, yeah, okay, that was a zoom line, cool. Then I will close the current example. We'll save it, maybe we need it again. Close it and open the next one. So I have prepared another example for the topic of data analysis. And let's have a look. Oh, we don't need that one anymore. Okay. So I will not guide you through again the whole procedure of vehicle data loading and putting in pictures. You know that already. It's quite straightforward. You just drag it in. However, this case is an interesting one because there is a lot of digital data involved, and data is getting more and more important. And I believe we will see, data in more or less every case in the future. Speaking about digital data, of course. This case is interesting, or especially interesting, because we have actually two sources of data. For the car, which is Audi, we have Bosch CDR data. And for the truck, we have a digital tachograph data. And we want to see how we can analyze this case using these types of data. You can also see there is a very beautiful traces, or the very beautiful traces on the ground. So that would be predestined to make tracking analysis, but that's not our task for today. We are going to focus simply on the data analysis. So what's happening here? According to witnesses, the blue truck came up here, this road, on the highway, and instead of like going first to the first lane and then to the second lane, he kind of pulled over directly over 2 lanes to the very left lane. At the same time, a very fast Audi came from here. You have to know this case is in Germany, I think, so there are no speed limits on this highway. So he is allowed to go as fast as he possibly wants or can. And they collide over here. We know that from the nice traces. And well, of course, the truck is much heavier, so the truck just brakes and has a standstill at some point. The the Audi rotates and ends in its final position. We can have a short look at some images. I'm opening a PDF right now. So I had to blacken a few things because that's, of course, sensitive data. But yeah, here we can see final position. That's not so interesting. But yeah, we can see, okay, this car is kind of heavily damaged. However, the actual only damage that comes from the collision is the one here on the front, because what happened here is that the fireman cut that part open to get the person out. The only real damage is here on the left front, which made that part fall down. And yeah, and with that piece of information, we want to start the case. Well, and the data that we got. Sorry. So the first movement we want to analyze is the one of the truck. In Europe, there is kind of over most countries a unique digital tachograph rule that is being enforced more and more. And that requires all vehicles heavier than 3.5 tons to have digital tachographs. Certain vehicles like military or police vehicles are excluded, but like the typical transporter you would see on the highway, that will have a digital tachograph. And this data can be read out, and we get it quite often. In most countries, it has the file format .ddd, but in some countries, like for example in France, it has a different format called .v1b or whatsoever. Doesn't matter, the files and the content are all the same. And we can read them in with Analyzer. So these data usually contain speed in a 1 Hertz frequency, so 1 speed value per second, which is not super precise, but it is like, yeah, better than nothing for sure. And in order to read it in, I'm going into modules, import driving data, and then DDD tachograph data. I have to load the DDD file. It asks me, because these files are encrypted, so it asks me if I want to also get a clear text file. I might need that for an appendix or whatsoever, but right now I don't need it. And then I can select of all the recorded data that is written in that truck. I'm selecting the last one here because that's the one where the crash happened. And you can see like the driving behavior for several minutes. It doesn't interest us for the whole process. It's only interesting for us for the last few seconds. So you can see here we have an acceleration, and then we have some deceleration. Since the mass of the transporter is so much bigger than the mass of the normal car, the collision itself doesn't really have an influence on the truck. So also you couldn't really like see it here because the resolution of this 1 Hertz data is just too little. However, we can assume that once the truck felt, at least he would have heard or felt something when the car crashed into it. When the truck felt the impact, he might have reacted and braked. So what we can actually do is we can say, okay, here around here must be his braking, the beginning of his braking. So he must have reacted 1 second prior to that. So if I'm now selecting a range like a little bit after and then a lot prior, I'm pretty sure that I can cover the most important parts of our pre-collision part. I selected that and I click on transfer. Like with every module, our main data window gets filled with data and we have a lot of acceleration, and in the end, we have some deceleration going on. We can immediately focus on some kind of synchronization because we can try to find out the impact point here. So we said when he accelerates, or like when he's on its highest speed value, and then he starts to brake, that means that 1 second prior to that, the reaction happened because he needs 1 second to react and then he can brake. So what I'm doing now is I am just saying, okay, this is position distance 0 and position time 0, which means that everything before that is a positive value and everything behind it is a negative value. That will help us with synchronization a bit later, because we should always take like the most important point, maybe the collision point, and work from there. Good. As before, we get a truck over here. I'm switching it on a bit more colorful so you can see it better. I go to second 0 and I move the whole truck in this position at second 0. Of course, I'm not really interested what happens after it. He will brake, but yeah, not so exciting. What it is interesting is the pre-collision movement we have here. So I'm again inserting a few more points and trying to shape the driving line how I think the pre-collision movement would have played out. So remember, we have people saying that he was kind of directly pulling through that line and going to the outer line. So maybe it could have been something like that. So now we have our truck coming from here, going up. Yeah, I could put a little bit more effort and love into that one. So maybe here. So going there, directly pulling over and going to the outer line. That's one possibility. We don't know if it's the right one, but one way to at least double check if that what we do has some kind of credibility is to look if it's even possible from a physical perspective. And in order to do so, I'm opening the coordinates window. I'll make it a little bit bigger. So this gives you a bit of information at every point of the movement of the truck. And one thing could be that this is not possible. This movement is not possible because the lateral acceleration would be a bit too high. So usually normal acceleration, like the top value of that would be 6 meters per square second lateral acceleration. But like in a that would be really like the one of the high, like a super high value. So that's not normal to drive like that. But in a way, how I shaped it, we have lateral acceleration of 0 something 2 meters per square second. So that's all in a very normal, decent range. So at least from a technical perspective, this pre-collision behavior is possible. Of course, we want to be fair and want to also see the other side. We want to see what, like, if the truck has gone like straight here and then out, and we see if that is possible. So what I can do in Analyzer is I can always do copies of vehicles to make alternative versions. So I'm going to vehicle number 3. I click on copy from 1 to 3 and OK. And now I have the exact same vehicle twice. I'm switching number 1 off and adjusting or building an alternative version with number 2, where he like first goes straight where he's supposed to be. Something like that. And then like goes out like here maybe. And then up here. So now its movement is like this and pulls over to the other one. And let's see also that is from the perspective of our normal acceleration is quite okay. So actually we cannot say like both versions are possible from a technical perspective, which is also sometimes the result. Good. Let's have a look at the second vehicle. For the second vehicle, we do have Bosch CDR data. I guess most of you will be familiar, but in any case, Bosch CDR is a tool by Bosch who reads out like vehicle systems, for example, the airbag module, and stores some data. And at least in the European Union, starting from, if I'm not wrong, 2024, every new vehicle must have a certain amount of data available for experts. But some manufacturers actually do it for quite some time already. For example, Toyota is like relatively freely giving out its data for quite some time. Other manufacturers like Tesla are notorious for not giving you the data. But you will encounter CDR data more and more, and it's definitely worth dealing with that topic. So we have a module that can read in this data, and that's called CDR data. And I am searching for the file, and it's important to know we don't read in the PDF file, but the software from Bosch can also create a CSV file, and that's the one we're reading in. And that reads in the data. We see there is some pre-crash data, there's some crash data, but we are interested in the pre-crash data today. The CDR stores up to 6 events at max. An event can be triggered through a collision, but also through a high deceleration or acceleration and so on. And if you have a close look, you can see that these profiles all match and are like one after each other. So this is actually the one where we have the first collision, and then the other ones are triggered through the skidding that happens a little bit later. So I'm taking the pre-crash data here, and it's always important to really carefully study data. So if you would just go in here and say, okay, and the last one is the speed where the car collided, you might make a mistake, because you see there is actually a huge gap here from roughly 200 kilometers per hour to down to 170. And that's not really doable in half a second. So it's kind of a good idea or like a hint to believe that the collision actually happened at this data point. So I'm going here. I'm selecting I want to have this behavior. This is pre-collision till crash, and everything after is crash. And again, I'm clicking on transfer. What I'm getting now, oh, whoopsie, I have written it on the wrong vehicle. I'm sorry, should have selected vehicle 2 here. Let's do this again. Pre-cache data. So vehicle 2, not vehicle 1, and transfer. Okay, so now we have our red one. Sorry that it all looks so small, but the road is so large. And I'm moving it over here. And actually turning it so it goes on the right direction. Adjusting the driving line a little bit. Also here in the end. Putting in another point. So we have this behavior as well. Okay. And then I can also synchronize the movement automatically again. And well, now we do have the pre-collision behavior of the red one as well. So they're going from here. He's coming from somewhere back there. Going. The one is pulling over. Red one is coming from the back and colliding. Good. So if we're looking at the kinematic data of the red one now, we can see that he was first accelerating and then decelerating at some point. So maybe this is safe to assume that actually the beginning of the reaction was when he switched from accelerating to decelerating. So 1.5 seconds before 0.0, which is our collision position. Let's have a look at that. So I can click on the clock and just type in 1.5, and that will show us the scenery 1.5 seconds before the collision. And well, if that is really the reaction point of the red one, we see that he should have seen the blue one maybe much earlier because he's already like mainly on that lane. And maybe he had reacted too late. On the other hand, let's check the truck. So, I mean, usually it's not allowed just to pull over 2 lanes. And we can check how or if the truck could have seen the red one. And what is usually a thing you need to do when you change lanes then is to at least look into your mirror. So let's put in the mirror for the truck. And I want to have the left outer mirror. Here in the settings, I can set it up. I haven't looked it up how that mirror exactly looks like, but if you're working on a real case, of course, you have to put that in. I'm just taking the default values now. I click OK. And I click OK. And that's okay. Probably that default value is a bit steep. I will not take that one. I mean, okay, we could play around now with the angles and so on. I will just change it a little bit so it looks backward directly. So you see, hope you can see that there is this triangle shape where the truck looks back. And we see that the red one is definitely, oh, maybe if it does like that, yeah, but it should be definitely in the field of view here of the blue truck, and he just shouldn't pull over like that. Okay, this is a short little example how we can work with data analysis in Analyzer. There are several modules designed for that. To finish off, we can have a little look in 3D, maybe. If it wants to start. Yeah, feel free to give me your questions, and let me know if something is unclear till now, or we can have a first look in that. So here we didn't work with a laser scan or 3D photogrammetry. Here we just worked with a 2D image, or actually several drone photos. And we can have a situation like this. We can also have a look from the perspective of the red driver, for example. Where you can see that how the truck went over. I mean, he was very far away. He was going with over 200 kilometers per hour. But it should be quite visible that such a truck is coming here. And yeah, and then the collision. Do you have any questions about that case? Anything that is unclear? Anything, that I can help you with? I can see. Okay, no questions right now. That means we can continue to the next example. Oh, there are. What are the options for nighttime collisions in terms of moderating lighting phase as a deliverable for the court? Can we show, for example, with just lighting available and to alter if the daylight? Oh, yeah, that's a good question. So let me show you that. So what we can do is we can first of all switch off the daylight if we want to. So drawing a night sky. So now we have night sky here. What we can also do is we can calculate how shadows are thrown. So I'll show you that in a second. I'm switching the shadows on. And what we have here is a tool for calculating the solar position. So I can say calculate solar position. I put in a date. So don't know, today is the 4th of September 2023. And let's say it's 4 o'clock. I know it's not, but or at least where I am, it's not. It's summertime. And then I have to put in the coordinates and the time zone, but there is a database included that contains several thousand locations. And I can just, like, since I'm Austrian, I'm taking Austria, of course. I'm selecting a region. Oh, okay. I shouldn't, maybe. Again. Okay, let's take a German one. Okay, maybe Bavaria. I'm typing in like a first letter, and it lists me up all the locations that start with that letter. So maybe I type in Munich or München in German, and it will immediately give me automatically the coordinates of that, how the shadow gets thrown at that time, and the time zone that is in, when the sun rise and sunset is, and so on and so on. So that's a way to work with light. But also, to be precise, what doesn't work and also won't work, because it's a kind of a different field of work, is that we'd make light analysis of specific type of vehicle front lights, because that's super different for every vehicle and you cannot calculate that in that sense. So that doesn't work. But the vehicles show like brake lights and so on. Yeah. So I hope that answers the question. Then someone asked, does it work for the 4 Hz tacho data too? Yes, it does. And I am a bit proud to say that we can read out all the file formats, also the new ones. So yes, it works also the digital tachographs 4 Hz as well. What about PTW? Do you have some example? I'm not sure what PTW actually means right now. Maybe you could precise that. Then I'm happy to answer. Oh, motorcycles. Oh yeah, we have motorcycles. Yeah, sure. I haven't prepared an example today though, but how you would work with a motorcycle is just you go here and select either you want to have a default motorbike, then you just take that one, or you go to the database. Database is much bigger for the cars than for the motorbikes, but there are some motorbikes inside, and then you can work with that as well. And one thing you have to be always aware of: kinematics doesn't care if it's a truck, a motorbike, a pedestrian, or whatsoever. Kinematics works for everything, and that's why it's so powerful. And we actually have a strong focus on kinematics and data analysis. But yeah, motorbikes are there. Okay. If there are no more questions about that case, I would like to continue. Yeah, we can save that as well. Maybe we want to have it later. And now I have, well, yeah, that's a very short example about only one module for serial collisions and whiplash syndrome. Depending the country you're in, you might see people complaining about neck injuries at court, but they're not big enough to like really show. But maybe also not small enough to really exist. In truth, I have made the experience that some people use that to try to get money out of a court case. But on the other hand, it can be very justified. And yeah, we have to deal with these topics from time to time. Of course, we are no doctors, so it would be wrong if we as traffic accident experts say, oh yeah, here he has a neck injury or not. But what we can do is we can analyze the accelerations a person I get someone's writing that never happens, false claims, no. Yeah, yeah, I have a feeling you know what I'm talking about. Okay, so what I have here is a crash test from Switzerland. I show you some images. Crash tests are great to like double check calculation results and learn from them. So there is a Mercedes Vito and a Skoda Fabia. Mercedes Vito is standing. Skoda Fabia is moving. And we know that the Vito is like, no, sorry, the Fabia is braking with 7.1 meters per square second before the collision. Yeah, we know that because of a crash test, of course. We'll see a lot of damages. It's very important to like analyze damages, not only on the specific case, but also to kind of understand how deep actually cars penetrate each other. I've made the experience with all the courses I've held in the past few years that people tend to actually underestimate how deeply cars penetrate each other, because a lot of parts of the car pop out afterwards. Like if you see that one on the top, you could say, okay, there is like, I don't know, 2 centimeters or something like that. But actually, in order to shape the front part like this and have this part, there needs to be at least a bit of a deeper intrusion. So yeah, this is my call for checking cars on a regular basis. You can see here is a metal part dented in a little bit. I just want to get through this quite quickly. So we have 2 cars prepared. We have a Mercedes Vito and a Skoda Fabia. And what I'm taking now is a module called serial collision that allows us to do serial collisions up to 8 cars. Usually you just have 2, but theoretically it's possible. And the speciality about that is it allows us to not only calculate collision speeds, but also helps us understanding accelerations that people that are sitting inside experiencing. Okay, so it looks frightening, but actually the only thing that interests us now are these 2 columns, because the rest is only if we have more than 2 cars. So deceleration at impact, well, that's the thing we know from that crash test of 7.1 and also after 7.1. The other one doesn't break, but we should give it, like, it needs to have something different than 0, so 0.5 or something like that, just to acknowledge that there will be some slowing down elements in the car. Then we have 2 values, out of which we need to put in 1. We have velocity difference after impact or the final distance. Final distance, the problem often is that when you arrive at the scene, you probably don't know them, or cars have been moved or whatsoever. But the good thing is velocity difference post-impact is usually in a range of 4 to 5 kilometers per hour. So usually safe to assume that. Okay. Then next step, we have 6 values here. ES value, deformation after the collision, and stiffness. So this is the tricky part. Because out of these 2 times 3 equals 6 values, we need to put in 3. And they don't have to, like, they can't be all from one vehicle, so they have to split up somehow. I don't know if all of you are familiar with the concept of ES. ES is a shortcut for energy equivalent speed, and is a concept that tries to capture the deformation energy in form of a speed. When it was originally invented, it was designed to be a control value. Some people use it rather as an input value. I would not recommend that, because if you do that, you easily make mistakes, because it goes into the equations with a square, and when you make a mistake with a square, it's a bigger mistake, obviously. But it's a good control value, so we will rather focus on the deformation after the collision. And why after the collision? That's because of the thing I just mentioned. When we would just like look at an image like this, we would say, oh, that's just 2 centimeters, something like that. In reality, it's a bit deeper intruded, because this metal part is bent up and remained bent up. If you can get your hand on the car, like remove a few parts, check which are the solid parts that are really dented in, so see how far the car was really like intruded, or yeah, by the obstacle. So for this case, I have of course prepared a little bit myself. Like I came up with something like 14 and 16 centimeters, if I recall correctly. Could be wrong now, or the other way around. I don't recall it correctly, but something around these lines. But the purpose is to show you how this works anyways. And then, so we have 2 values. We need a 3rd value, stiffness in kilonewton per meter. So this is an average stiffness over the like deformation distance. Usually you have something between 700 to 1,400 kilonewton per meter, but again, that's up to you. And it's depending, are softer parts involved, are harder parts involved. If some steel part was involved, it's definitely harder. If some plastic was involved, it's definitely softer. So I might give that one like 700 kilonewtons per meter. Last but not least, we have these four values: velocity pre-impact and coasting velocity. Fortunately, we only need one of those. And since the front one was standing, 0 kilometers per hour is a valid input. So we can just click on calculate. What do we get? We get the pre-collision speed. We get maximum accelerations of the cars. We get K value, we get the impact duration, we get how long the compression phase was. So a few things that might be interesting for a report. Also, it's shown here. But what's actually a bit more interesting is the following part. So, and that's the passenger stress part. Opening that one. So what happens when someone is sitting in a car and gets hit from the back is that the person is first getting pressed into the seat, into the like soft parts, cushion, whatsoever. Then in a second step, the back of the seat might bend a little bit. And then, well, then usually we are not talking about whiplash anymore, but then it might like really permanently bend, and then it might rip off. We're not talking about these areas, but just to give you an idea. So the person is sitting on its seat, it's going to be pressed in, and after a certain amount of time, the seat is going to push the person out again, by like and acting like some kind of a spring, if you want, and that gives the person some additional relative acceleration, because usually the body is sitting on a seat and the head is not, so the body gets over proportionally accelerated, and that's supposed, as far as I understood, the reason why people might experience whiplash syndrome. Fun fact on that side, if you look way back, the seats in cars were super soft, like with super soft cushions, and because people thought that's actually safer, and then they found out it's not, because they might have a first softer impact, but then they get thrown out like crazy from a spring. So at least that's the story I heard about that. Maybe it's wrong, I don't know. Anyways, we can put in here parameters for the seats. If you have like a super picky case, you need to do your own measurements. But usually, like for default, that works for me, because we just want to make like getting close ideas. And I can click on calculate. So what we see here now is a maximum, like a mean value of the passenger and the vehicle. That needs to be the same, because on average, passenger and vehicle get accelerated at the same amount. But the maximum value, the peak, that's much higher. So that's almost 8G compared to 6G for the car itself, because the driver, or the person we are referring to, is kind of sitting on a spring, aka its seat. So the maximum acceleration can get higher than the car, and that's a thing you can calculate with this module. You don't have to. You can also just use it for these typical rear-end collisions that happen probably on a daily basis everywhere, just to find out impact speeds. But yeah, that was another little part of Analyzer I wanted to show you. Do you have any questions about that? I know it's a lot of information by now, and it's a long monologue from my side, but we're almost done. There's one more example left, and then we're good. Okay, if there is no more question, I will continue with the next example. Oh yeah, can I ask if there are any independent white papers on any of the modules? Not meant in a critical way. Well, it can be meant in a critical way. It's important. There are papers on us. I am just like in some of them we are involved. Actually, right now we are working with someone from the States on the crash test of Rex. But I can't point you towards one that I can recall right now. I know there are a lot of there are some master theses and that kind of stuff, and there are mentionings, but there's not the paper that says I'm going through the modules and checking them all through. I think that doesn't exist, but feel free to. You're very, very much invited to do so. We are publishing at SAE a paper soon-ish about Rex. Yeah, so, but if you are involved in some kind of research, happy to support you with Analyzer, and of course, happy to if we get tested properly, we are, of course. But yeah, we do our own crash tests on a side note. That will be very interesting, the SAE paper on Rex. Yes, it's a process, but I would say we are like 60% through. Anyways. Good. Speaking about Rex, those of you who aren't aware, there was an event at Orlando in April in the States, and we were there. It was great. And there were, amongst other things, crash tests, right? And the last thing I would like to show you for today is our video analysis module. You know, CCTV is becoming more and more important. There are different sources of videos and so on and so on. And what I would like to show you is a module now that helps us to track or to analyze videos of static cameras. And I will just load a video. Those of you who were present might recall this. This is the case where a Volvo collided with a Chevrolet. For some reason, they put a large amount of water in the back, which is a bit annoying because you can't see anything of the footage when they collide. But fine, not my decision. Anyways, on top you can see the original video that was, I think, done by a drone. And what we want to do is we want to find out the speeds of the cars involved. Good thing is we already know them, so there's a way of, it's a way of double checking. First step we need to do is we need to rectify that video. The rectification happens in the bottom video, so we need to put in some shape. It doesn't have to be a rectangle. It can have any shape where we know the distances. So if you are working on a real case, make sure you find 4 points and measure the distances between them, and then you're good. So I have written down before in preparation for that 10 lines of this 1, 2, 4, 5, 6, 7, 8, 9. So one more 10 lines of this crosswalk. So I'm adjusting the points up there. Then I have to put in the values. So from P1 to P2, it's 8.52 meters. and for the other one, it's 4.85 meters. Okay. So what you can see down here now is a rectified image or video, and on top you can see the original video. This rectification works with linear, like regular lenses, but it also works with fisheye lenses or wide-angle lenses, which is cool because usually you don't know the data of these lenses, but we can automatically calculate them out of the video, and then you can still work with like barrel distortion or cushion distortion anyways. Good. So what I will do now is it will detect all elements like vehicles, pedestrians, and so on in a certain pixel size. And since I already know the car is going to be very small here, I'm decreasing that a little bit. And then I can just click play. And you see the algorithm immediately detects all these people and this car and so on. That's not really interesting for us. But yeah, at least you get an idea what's happening. So the algorithm detects these the elements, in this case, these people. The people are moving, and it stores the speeds. Unfortunately, we have to wait a little bit now because here on the left we can see the car that drags that pulls the colliding car and accelerates a little bit. And in a few seconds, our colliding car, I think it was the Volvo, will come from up here and go downwards. We have presented this tool at last EVU conference a year ago, also like double checked with speed tests, and we found out it's pretty accurate. It's not super accurate, like not that you can say it's 50 or 51, but it will give you a very decent like idea about the speed the car or the whatever you want to check was moving. So here we have our car. It gets detected, and we will see some speeds. Don't be confused that they jump around a little bit. It does a calculation with the pixels, and that's not in the moment not always super duper precise, but you will see in a second how we even that out. There comes the second car, and they collide, and yeah, soon after we won't see much because there's water inside and it will splash all over. So we have to remember now this car has the ID number 10. So I'm selecting ID number 10 here, and we can see the speed of the car. The red line that's going a little bit zigzagging up and down is the one that we measure frame by frame. And the blue one is a fit curve that should give you like a smoother driving behavior. And as before, we can just select a certain range and we can transfer that, and we have it immediately in our kinematics window, in our main window, and can continue working with that case. You might ask, how precise is that? I have done a comparison on that case because we had some CDR data from that one, and you'll see it in a second. So here, the red one is, or the orange one is the one from CDR data, the gray one is the frame by frame, and the blue one is the fit curve. So you can see it's it's not super precise, but it will give you a decent idea where to search for, in which area you have to work. And you can at least be very sure that this car was not going with 30 kilometers per hour. So again, a tool to get an idea about the speed, not to make super precise speed measurements, but better than nothing, I'd say. Good. Once you have that, you can click on transfer. And like before, we will have data in our main data window. It's written inside there. We can see our coordinates. We can let it drive in the same way. And we can continue our case from there. And that was kind of it. A very short presentation about some features. Analyzer is a huge piece of software. I could talk for days and still could show you new stuff. But yeah, there is plenty to show, and I hope you enjoyed it. Please give me your questions if you have. And I read already, is there any option to confirm alter the varying frame rate of the video? Yes, there is. So there is a thing called frames over here. And here is the measured frames. And we could put in selected frames because sometimes this measured frame rate is not correct. It can be that you have to correct that. And then you could just, instead of measured values, put in selected values, write in which ones you want to have and see how the speed adjusts and use that piece of speed. Is there any idea on the length of the training required to be competent in the basics? I think it's very simple, actually. There are a few things in Analyzer that we strive for, and one of them is to make the software, like to learn the software as quickly and as easily as possible. Analyzer follows different approaches than other softwares on the market. So if you're used to some, you might have to rethink some of the concepts. But if you sit down and put in an effort, you will get a pro in a week. If you want to do it slower, like there are free video tutorials. There's another thing I can show you. There is a tool called the Analyzer Assistant that helps you like with clicking through and highlighting elements, and shows you, okay, now you want to do a collision analysis, click here. What do you want to do? Now click here, and so on. So we're really striving to make it as easy as possible. Usually, of course, it is an effort. This is not Microsoft Word. I agree. I agree on that. But usually, if you like used to working with software, if you have an idea about traffic accident analysis, then it shouldn't be much effort. We have actually prepared a special offer for the participants of that course that let you dive into Analyzer if you want to. And that's, oh, I hope I have that on the laptop now. Give me a second. Otherwise, you'll get it via email later. Wait. I'll have that in a second. So essentially, we have an offer that allows you to use. Oh yeah, there it is. There. Special offer. Essentially, it allows you, or it gives you free access of Analyzer for over a month. It gives you video recordings of a 4-part basic course. And then on these dates, we will have a live 4-part advanced course via Zoom. That costs a little bit, but the whole package together only costs you the participation of the advanced course. After that, and if you put in a little bit of effort, you should be like super ready to work. If you really want to go through it within a week, you will be, yeah, you will be a professional, I feel. We spent the last 7 years, I'd say, when I took over, to make Analyzer as user-friendly as possible. There are limitations, of course, because it's still a complicated matter we're dealing with. Yeah, that's roughly it, I'd say. Of course, I would be happy to see as many as possible of you. And if you can't make it on these dates, just write me an email. We can arrange that you get the video recordings. Yeah, but people usually say it's easier to use than other pieces of software in that field of work. Are there any further questions? If that is not the case, I thank you for your attention. I know it was a lot of information for 2 hours straight, and you're all probably tired now. However, we have recorded this meeting. We will post it on our LinkedIn, and we will send it out in our newsletter, so you can rewatch it. I would be very happy if you could share the information about us with your friends and colleagues. And yeah, if there are no more questions, thanks again. Have, in my case, lovely evening, but might be different for you. And yeah, have a good one. Bye-bye.